Okay, this is section 6.5 in your textbook. It's on page 350. We're looking at exploring graphs of the reciprocal trigonometric functions. So before we start this section, we need to be familiar with the original trigonometric functions. The first one you can see here, which is sine theta, y equals sine theta. So as we know, sine theta, y equals sine theta, the x-intercepts are at 0, theta, and 2 theta. Again, that's because 2 theta is equal to 360. We know sine 360 is 0. Sine theta is equal to 180. Sine 180 is 0. So that's also our x-intercepts here. Likewise, you can see the other standard trigonometric functions here in blue. So y equals cos theta is this blue line here, again starting at 1 on the y-axis and kind of proceeding similar to the sine theta, except the difference is that it starts at 1. And finally, the last original trigonometric function is y equals tan theta, which you can see in blue or purple over here. Y equals tan theta. Okay, but we're interested in finding out today, the goal is to graph the reciprocal trig functions and determine their key characteristics. So the question is, what are the graphs of y cosecant theta, y secant theta, and y equals cotangent theta look like? Okay, and as we know, these are just the reciprocal functions. So this graph, y cosecant theta, is the same as y equals 1 over sine theta. Okay, this is y equals 1 over cos theta, and this is y equals 1 over tan theta. So what we're trying to figure out today is, what do these graphs here look like? Alright, so the first thing we need to do, recall that the characteristics of the reciprocal functions are directly related to the characteristics of the original function. So what that means is, we can look at the original functions and by observing the original functions, we can see what these functions are going to look like. Okay? And that's directly from section 5.1, when we were dealing with quadratic and linear functions. Okay? So the same applies to trigonometric functions as what applies in 5.1. So we're going to use a lot of information from 5.1 for this particular section, so it might be worth reviewing some of the key points in 5.1. Alright, so therefore, we want to learn about the graphs above. We will first recall the original functions of y equals sine x, y equals cos x, and y equals tan x, or tan theta. So we're going to focus on y equals sine theta first. Y equals sine theta, as we know, looks like this. Okay, there's our graph y equals sine theta. Again, we are putting the units of the x-axis in radians as opposed to degrees, okay, which we should be familiar with by now. The vertical asymptotes are the first thing we want to use as a hint when graphing y equals cosecant theta. Okay, and we know vertical asymptotes occur when we have a situation of 1 over 0. Y equals 1 over 0. So using that logic then, we know that our vertical asymptotes occur when sine theta equals 0, or y equals sine theta is equal to 0, which is, coincidentally, the x-intercepts of the original function. Okay? So at these points, we know on y equals cosecant theta, there has to be vertical asymptotes at those points. Okay? And that's because of the logic of y over 0, which we know occurs when there's vertical asymptotes. Alright, the next thing we want to look at is, when do the max values occur? Okay, and as we learned in 5.1, the max values of the reciprocal function occur when the minimum values occur on the original function. Okay, and vice versa. The minimum values occur when the max values occur on the original function. So this point here, which is a minimum value on the original function, is going to be a maximum value on 1 over sine theta, or cosecant theta function. Okay, so it's a minimum here, but on our new graph it's going to be a maximum. So we have to have some sort of parabola happening like this. This is a minimum. We're going to see a maximum. We're going to see a minimum on our new graph. All right. And this again is just from 5.1. This is review from 5.1, reciprocal functions. Same thing applies for positive and negative intervals, like we learned in 5.1. Any of the areas that were positive on the original function, so these areas above the x equals or y equals 0 axis, x-axis, are positive on the original function, they're also going to be positive on the reciprocal function. All right? And then finally, we talked about intervals of increase and decrease. Remember, an interval of increase is basically the slope of the tangent. If the slope of the tangent is moving up, it's an interval of increase. If the slope is moving down, it's an interval of decrease. Okay, so between this area and from here to here, all of these tangents are decreasing. So this would be an interval of decrease. Okay, so the opposite is going to occur on the reciprocal function. There's going to be, in that particular area of x values between negative 3 over 2 pi and negative pi over 2, we're going to have increasing. Remember, always reading from left to right. Okay? And finally, the last point, again from 5.1, is that the points of intersection of the original and reciprocal function occur always when y equals 1 and y equals negative 1. Okay, and the reason for that is because we're taking the reciprocal function. So when we have our reciprocal values, 1 over 1 is just 1, and negative 1 over negative 1 is negative 1 as well. So that's the reason for that, because our reciprocal y values are equal to the reciprocal of the original function y values. Alright, so taking all that information now, we're going to attempt to graph 1 over sine theta. Okay, so we learned that the vertical asymptotes occur when the x-intercepts are happening on the original function. So we know that there's a vertical asymptote at x equals 0, x equals pi, x equals 2 pi. So those are the first things I'm going to draw in here. I draw it at x equals 0, x equals pi, 2 pi, I draw in my vertical asymptote lines. Okay. Next thing, I know that I have max values at minimum points. So when I had a minimum point here, I know it's going to be a maximum point here. So that same point, again, because that point is also at y equals negative 1, I know that my two graphs intersect. So my original function graph, my y-coordinate point, is going to be the same point as on my reciprocal function graph. Okay, so anywhere where there's a y equals 1 or negative 1, those are where the old graph, which is here in blue, the original trigonometric function, intersects with the new graph, the reciprocal trigonometric function. Okay, so you'll notice that on all the graphs. Anywhere where there's y equals 1 or negative 1, that's where the old and the new graph share the same point. Okay, so we know that where there was a minimum value here, there's now a maximum value, so I have to move up down there. Where there was a maximum value, there's a minimum value. Alright, so that takes care of B. So these points here are dictated by max and min, as well as our E point. So we're using B and E to create these points, these maximum and minimum points. Finally, where I had positive and negative intervals, they're the same on both the originals. So what was positive values of y on the old, so I'm above y equals 0 here, I have to also be above on the new or the reciprocal function. Okay, so that's why all my above values y stay above y, all my below values of y stay below y equals 0, so they stay negative. So they're negative, they stay negative, they're positive, they stay positive. Okay, so the same thing happens with the cosecant function, the same thing is happening with the tangent function. So where I was positive on the original, which is in dashed blue, I'm now positive on the new one in black. Intervals of decrease occur during intervals of increase on original function and vice versa. So this is kind of the final point where I know to draw these lines the way they are, because I know where it was increasing on the original function. So looking at the blue graph, I can take a slope here, and I know that this is an increasing interval. On the old or on the new graph, it needs to now be decreasing. Okay, so the original trigonometric function, the interval was increasing here, it needs to be decreasing. So here it's decreasing, on the new, it's increasing. So old here is decreasing, and new is increasing. Okay, so that's what the intervals the intervals of increase and decrease are referring to. Okay, so that's how we end up with this final drawing. Okay, we have our vertical asymptotes, which is the first thing we find. We have our intervals of increase and our intervals of decrease. We have our positive and negative intervals, which are the same. And then we know that the old and new graphs intersect where y is equal to 1 and y is equal to negative 1. Alright, so just to summarize y equals cosecant theta, we have vertical asymptotes at points where sine theta is equal to 0. Again, that's because y is equal to cosecant theta is the same as 1 over sine theta. We know we get vertical asymptotes when we get 1 over 0. So that's why we have vertical asymptotes at sine theta is equal to 0. To find those points, we look at the original function. We see all the values where y is equal to 0, which is here, and those become our vertical asymptotes. Next, we know that our period always remains the same. We learned that again in 5.1, that our period for our original function and our reciprocal function is the same. In this case, the period is 2 pi. Again, just to review, period is the value of x at which point the function starts repeating itself. Okay, or one complete cycle. The domain now. The domain is XER, all real numbers. We're extending in this direction. Okay. We're extending in this direction with our reciprocal function. And theta cannot equal n theta. And what that means is where n are elements of integers. So n are integer values, so they're whole numbers. So theta cannot equal 0. If theta is equal, if n is 0, n cannot equal 0. If n is 0, this expression is 0, so theta cannot be 0 because the vertical asymptote is n is 1. Then we would get theta is equal to pi. When theta is pi, we have another vertical asymptote. So that basically this domain here, we're finding all the areas of theta where the vertical asymptotes are. That's where this n theta comes in. So now if you use any integer for n, you're going to have a multiple of theta. And that gives us a vertical asymptote. So 0, theta, 2 theta, 3 theta, etc. So n represents integer values. So 1, 2, 3, 4. And that represents our vertical asymptotes, which are also no-nos for our domain. Okay. Finally, range, we're looking at YER, so all real values of y, where y, or absolute value is y, is greater than and equal to 1. It's another way of saying where y is less than and equal to negative 1, or y is greater than and equal to positive 1. Okay, you could have used this range or this range. Remember, when we have an absolute value, this is positive and negative y. Being greater than or less than 1, we would have to switch the signs direction if we were to divide by negative 1. That's what gives us these two values. Okay, so that's y equals cosecant theta. It's here in black. So we're going to use the similar approach to figure out y equals secant theta. And y equals secant theta, remember, is the same as 1 over cos theta. Okay? So using the same logic now, we know that vertical asymptotes occur where the original function of cos theta is equal to 0, because then we would have 1 over 0. So anywhere where we see the value of y being 0 on the original function, again, this dashed blue line being the original function, those will be vertical asymptotes on our new function, or our reciprocal function. So we cross through 0 at this point, which is pi over 2, at this point, which is 3 pi over 2, and at this point, which is negative 3 pi over 2 and negative pi. So those points that were 0 on the original function in blue, they become our vertical asymptotes now for our reciprocal function. And again, that's from the idea that y over 0 is an undefined value, is where the function cannot have a value. So that's why it's a vertical asymptote. Okay, so that's our vertical asymptote. The next thing is our period is always the same as the original function, so it's 2 pi. That's the point at which it starts to repeat itself. So you can see from negative 2 pi to 2 pi, this range with this domain, we start to repeat ourselves. Okay, so from this point on, we're going to have an identical repeating pattern. So domain now, similar to the domain for y equals cosecant theta, we have xer. Theta now cannot equal 2n minus 1 times theta over 2. So this seems complex, but again, n is just integer numbers. So increasing by whole numbers, if n was 0, this would be 0 minus 1 times theta over 2 would be negative theta over 2. So that's definitely an area where theta can't be. If n was 1, we would have 2 minus 1, so we'd have theta over 2. So that would be this value here. So domain, again, we're trying to find the values where theta, or the x values, are not valid. So we have theta over 2, 3 theta over 2. This equation allows us to express that for all values where n are real integers. Okay, so that's where that comes from. Range, again, very similar to y equals cosecant theta. We have y is all real numbers, where absolute value of y is greater than and equal to 1. Or, as I said in the last example, y is greater than or equal to 1, and y is less than or equal to negative 1. Alright, so that's our y equals secant theta graph. Finally, the last one, y equals cotangent theta, is here in black. Again, it's the reciprocal function of y equals tan theta. So in other words, this is equal to 1 over tan theta. So, using the exact same logic, we're going to find our vertical asymptotes where our original function, tan theta, was 0. That's where our vertical asymptotes will now be. So our original function is here in blue. So where they were 0, they crossed the x-axis here. That's where now we have vertical asymptotes. So right here we have a vertical asymptote at negative pi, negative 2 pi, pi over here, and 2 pi here. Okay, so those are our vertical asymptotes now. We have zeros at points where y tan theta has a vertical asymptote. So on our original function, so we're using the same logic but going reverse. Our original function, we had vertical asymptotes at the points where now on our new function we have zeros. Okay, so there would actually, on the original function here, there was a vertical asymptote at this point, there was a vertical asymptote at this point here, and now those become our zeros. So using the exact same logic here, just flipped over. So where we had vertical asymptotes, they become our 0 points on our new graph. Alright? We have the same period as pi, as y equals tan theta. So after 1 pi, we have a repeating pattern. So that's all we need. That's our whole period right there. And our domain is xer, where theta cannot equal an integer multiple of pi. So just like we have pi, we have a vertical asymptote. 2 pi, we have a vertical asymptote. So that's why we cannot equal an integer multiple of pi. And our range is yer. We're hitting all the values of y. Alright, so looks complicated. The theory is all the same from the original function. A lot of it is taken from 5.1. It took a long time to write out, but I don't think it's actually that complicated. The first homework question is a little confusing. I thought I would just take that one up to get you guys started. So it reads the equation Tn. So here, Tn equals a plus n minus 1 d can be used to represent the general term of any arithmetic sequence where a is the first term and d is the common difference. Okay, so we use this equation to find an expression that describes the location of each of the following values. So this is the graph that we're considering. And it asks us for, we need to represent the vertical asymptote values in this type of equation. So the first thing we want to do is look at this graph and see where do the vertical asymptotes occur. So we're going to go to this graph, which is right here, and we see the vertical asymptotes occur at pi, they occur at 0, negative pi, and 2 pi. So here I write down the vertical asymptotes of y equals cosecant theta occur at 0, pi, and 2 pi. So I have those written down. So now to create that equation, I'm going to use my first term, a. So my first term is going to be pi plus n minus 1 the difference between the terms. So the difference here we can see between 0, pi, 2 pi is pi. So n minus 1 times pi. So my first term is pi, my first term that has a value, and then my difference is pi. So pi plus n minus 1 pi, I multiply pi times n and pi times negative 1. I get pi plus pi n minus pi. These pi's cancel, and I'm left with pi n. Okay, so that's my general term for the vertical asymptotes. Next, it asks for the max values, an expression for the max values, and an expression for the minimum values. If I look at my graph, I see that there actually are no max values. Although these are local maximums, they're not absolute max values. So the answer would be no maximum values, and very similarly, there would be no minimum values, because again, these being local minimums, they're still not absolute minimum values. Okay, so hopefully that clarifies the first question. Questions 2 and 3 are similar to the first one, and question 7 take us back to transformations, now just using the new graphs that we've learned. Okay, so hopefully 6.5 goes well, and I'll see you later.